Hello and welcome to our lesson on secant and cosecant functions. We're going to get right into it here, starting with our parent form of the secant function, which is y equals the secant of x. Now before we graph it, which we're going to do by making a table because it's a standard way to graph any function, especially when we don't know where it's coming from, we got to remember where secant comes from. Secant is just the reciprocal of one of our other trig functions. Hopefully in your head you're thinking to yourself, oh, yep, I remember secant is the reciprocal of cosine. So since the secant is a reciprocal of cosine, we could also write it in the form 1 over the cosine of x. And in fact, if we were to put both of those functions in the calculator, we would see the same graph twice. But I don't want to spoil the fun. Let's not put it in the calculator just yet. Again, let's try to make a table and see what's happening here. And then if we need to, we'll go to our calculator. So we're going to go around the unit circle. Remember, when we're inputting x values, these x values that we input, those are angles. And the outputs that we get back out are the secant of those angles. So these are going to be secants of the angles here. So let's go ahead and start at an angle of 0 radians. So we're looking for the reciprocal of cosine. Cosine's the x value in all these coordinates. So let's look at that x value and flip it over. So at 0, the reciprocal of 1 is going to be 1. And then I don't necessarily want to have to graph these fractions if I don't have to. So I'm going to skip down to the next nice one right there. That looks pretty good. At pi over 3 radians, the reciprocal of 1 over 2 is going to be 2 over 1, so 2. And I can jump to this next one. What's going to happen here? At pi over 2, when I'm looking at the reciprocal of 0, so 0 is technically 0 over 1. If I flip that, I end up with a 0 in the bottom of the fraction, which means at pi over 2, our graph is going to be undefined. An undefined portion of our graph. I don't know if you recall what's going to happen when we have a 0 in the bottom of the fraction, or that undefined part of our graph, but it happened in college algebra with our rational function, so maybe you remember the asymptote concept, but we'll come back to that. So let's skip to this one. That's going to be at 2 pi over 3. I can take the reciprocal there and get negative 2. And then I can skip here. That looks pretty good. At pi, the reciprocal of negative 1 is negative 1. And then I'm going to jump down to this one at 4 pi over 3. Then we're looking at negative 2 again. And then at 3 pi over 2, the same thing happens that happened at pi over 2. We flip over 0 and we get something that's undefined. So 3 pi over 2, undefined. Okay, and then if I go here, we're good. At 5 pi over 3, I get a positive 2. And then full circle, back to 2 pi, then I'm back to 1 again. And I don't know if this is enough for me to make the picture, but I can try. Oops, I can try. So let me plot what I have here. This is 0, 1, we're going to have a point. At pi over 3, so a third, this is 1 pi here, right? At about a third of that, so if I was cutting this, maybe it's going to be something like that. A third of it, we're going to be up to 2, so maybe somewhere around there. And then at pi over 2, we're undefined. So what's going to happen at pi over 2 is we're going to end up with an asymptote. Okay, if we're undefined there, let's just put that little barrier and say, hey, a graph can't go here, can't have that input. Okay, that's what the asymptote is saying. 2/3 of the pi, so that's going to be around here-ish. Then our graph's going to go down to negative 2. So somewhere like here-ish, whatever, okay. I don't feel like that's a little bit off, but maybe like right here. And then at pi, we're at negative 1. That's a nice point I can graph. And then at 4 pi over 3, so that's going to be like here-ish, we're going to be back down to negative 2, or to negative 2. 3 pi over 2, we're undefined. Again, graph can't go there. We're going to use the asymptote and say, okay, let's put this dotted line in there. A dotted line, because it's not part of our graph. It's just saying, hey, graph can't go there. And then at 5 pi over 3, we're going to be at 2. So 5/3 pi is going to be somewhere like here-ish. We're going to be like right there. And then at 2 pi, we're going to be at 1. So something like this. Now, what is happening? It's a little hard to see, right? So we might want to take some of the other values for cosine, flip them over, make some more decimals here. I think the easiest way to flip them is to, instead of looking at them all in the unit circle, is let's look at them on our graph here. So I'm going to graph cosine Once I have all of those cosine values on my graph, I can flip them from my graph. So I don't know if that makes sense what I'm saying, but here's what I'm going to do. I'm going to graph cosine, okay? So cosine starts at 1, ends at 1, and then hits the minimum of 1 in between, and then has zeros in between those. So this is what, and I'm going to do this with a dotted line because I don't want this to actually represent my graph. I just want to kind of use it to help me graph. Okay, here's my cosine curve. All of my points on my secant curve should be the reciprocal of the points that are on this curve, which is why the secant had a point here, because the reciprocal of 1 was 1. And we had a point here because the reciprocal of -1 was -1. And we have a point here. The reciprocal of 1 is 1. Now, this is also why we had the asymptotes at the zeros, right? The reciprocal of 0 being undefined, we see those barriers there. So let's just flip a few other of the points. And maybe this makes sense here, where at a half, if I flip that, that's why the graph goes up to 2 here. And then the same thing at the other half, and then -2, and then over here we're at -half, and then we get -2. So we've already got those points flipped. Let's just try to flip a few more. So I'm going to use my highlighter to try to show you where I'm looking, okay? If I was to flip this point, the fraction is pretty close to 1. So like the closer I get to 1, like let's say my fraction is 8/9, like really close to 1, or maybe 9/10. When I flip those, I'm still pretty close to 1. Like 9/8 is just a little more, and then 10/9 is just a little more. So my graph is just going to be a little higher if I flip it. And then the opposite thing is happening over here. If I have a fraction that's closer to 0, like maybe I have 1/10 down there, then the reciprocal would be 10, which would be way up here. Or if I go really lower here and say that maybe that's like 1/100th, then the reciprocal would be 100/1, right? So it's going to go higher and higher and higher. So on this one, on this side over here, and I'm making a mess of my picture, what's going to happen is as our fractions get smaller this way on that cosine curve, the reciprocals are going to get larger. And I erased my point. So on this side, we're going to be getting closer and closer to that axis. The smaller my fraction gets, the closer I get, and it's going to get infinitely close to that asymptote, okay? Because I can get infinitely smaller fractions closer and closer to 0. And then the same thing is going to happen on the other side. If we flip all these, we're going to be approaching the asymptote here. And then we flip all these and we approach the asymptote here. And the same thing is going to happen over here. So our secant function is actually the part that I drew in blue there. So if I was to graph this in Desmos, and boom, there I see it. Okay, so I see like a half of a parabola on the outsides there, and then that parabolic piece in the middle. That is our secant function. And again, it's really helpful if you just put the cosine in there. Y equals the cosine. Oh, I forgot my equal sign. Because they're directly connected. All the points in cosine flipped give us the graph for our secant. Okay, so let's try to generalize a few things. This is a little strange, but this is not a continuous graph. We see the vertical asymptotes. Those happen when our cosine of our angle is 0, because when we flip 0, 0 on the bottom is undefined. And where does the cosine end up being 0? We talked about this. At pi/2, 3 pi/2, 5 pi/2, it would keep happening at those odd multiples of pi/2. So this is where x, well, let's be consistent with variables here. When the cosine of x is equal to 0, the cosine of our angle is equal to 0, we're undefined. And that's for x values that are odd multiples of pi/2. So this is where x is equal to, remember, 2n plus 1 guarantees we get an odd, and then we multiply by pi/2. And technically this is n is an integer, and we talked about that previously, so hopefully you remember those are where our zeros happen for cosine, which is where our vertical asymptotes are going to happen for its reciprocal. So in between the asymptotes, there are parabolic pieces. We can call them parabolas. I don't know if that's exactly correct, but they look parabolic, okay? So there are these parabola-like shapes in between those, and the vertices of those parabolic pieces are actually the maxes and the mins of cosine. So the maxes of cosine, we have, oh, that's my eraser. We had here and here, that's a vertex, vertex, and then the min, vertex. Okay, so those maxes and mins are where we're going to put our vertices of our parabolic pieces. And vertices of the problem max and min points of, oh yeah, cosine, sorry. Like, what did I mean to put in that blank? Of the cosine of x. All right, period, still 2 pi, just like cosine. That should make sense. That's how long it took for the one cycle to happen. For us to see the pattern would start to repeat once we go back around the circle. But unlike our cosine curve, sine curve that we've talked about so far, we don't have a max or a min. Those parabolas up at the top there are going to go up forever. The parabola down at the bottom there is going to go down forever. So there's no max, no min for secant. There is obviously for cosine, but not for secant. And because there's no max or min, there's no amplitude. So a lot of the terminology from before does not apply here. Now let's talk about the domain. For cosine, we can plug in whatever angle we want here. For secant, we can't. We said our angles can't be those odd multiples of pi over 2 because we'd end up with the 0 in the bottom of the fraction. So for our domain, we have to restrict those. So we're going to say the domain is all x's such that those x's cannot be odd multiples of pi over 2. So we can't be 2n plus 1 times pi over 2. And that's the set notation for that domain, probably the easier way to say it. Remember, this is n is an integer. I should have put that in there, sorry. And then let's look at the range. So the range for cosine was everything between -1 and 1. The range for secant is everything outside of -1 and 1. So the parabolas go up from 1 and down from -1. So the range here, which we can do easily in interval notation, would be everything from negative infinity up to -1, united with everything from +1 to infinity. But we have a gap in between the -1 and 1 where the cosine is. There's no secant function in there. Okay, and the secant function is an even function. It's going to have symmetry about the y-axis, just like the cosine. Should make sense. It's kind of mapping along with what it's doing. And that means when you plug in a negative angle, you get the same. So we take like the secant for pi over 2 and negative pi over 2, we end up with the same thing. So whether you plug in the positive or negative, you end up with the same result, just like our x squared. Okay, something we've talked about before. But the goal is for us to be able to take any secant function and graph. So how do we do it? Again, because it's directly connected to our cosine graph, that's what we should do. Let's graph the related cosine function and then use that to flip our points. So even though all of our transformation rules apply, we're going to start by graphing the related cosine wave and then flip those values, okay? So let's pretend we want to graph y equals 1 plus 3 secant x over the interval from 0 to 2 pi. Let's focus on 1 plus 3 times the cosine of x over that interval first. So if I was going to graph 1 plus 3 times the cosine of x, I know I'm going to be shifting up 1. And I know I'm going to have an amplitude of 3. And my period's not changing. My period's still going to be 2 pi. Everybody's okay with that, I'm hoping. So if I was to graph this, I'm going to shift my midline up to 1. There's that. That's going to be my reference line instead of my x-axis. And cosine is supposed to start at its I'm so sorry. It's supposed to start at its maximum. If I'm just looking at my graph and it's like the axis are not what I wanted to do here. So I'm going to relabel this. I'm going to call this 1, 2, 3, 4, 5. And then this is still 0. -1, -2, -3, -4. Just ignore this, okay? Don't know what I was doing there. So we're going to shift up 1. Amplitude going to be 3. So from the midline, we're going to go up 3 and down 3. And that cosine, remember, starts at its maximum. It's just 1 higher than it was before. So for up 3, we're going to start gosh, now hold on, gotta change my color. Get rid of this. No, it still looks like a point. It's gonna look like a point on my graph. I'm so sorry. Hang on. Let me use a white pen and just say, okay, don't want that to be there. All right, so now I'm in business. Let me try to graph. So cosine's going to start 3 above the midline. 1, 2, 3. So it's going to start at 4 instead of starting at 1. So the max is normally 1 plus the shift and the stretch of the graph. And then it ends at the same same place. So we're going to end at the same place. It has 2 pi, one cycle in there, and then it's going to be minimum in the middle. So at pi, we're going to go to our minimum, which will be 3 below that midline. 1, 2, 3. So it's going to be there. And then in between those, normally we'd hit the x-axis. We're going to hit the midline. So at pi over 2, we're going to be hitting the midline. 3 pi over 2, we're going to hit the midline. And that is my cosine curve that has an amplitude of 3 and is shifted up 1. So what I'm going to do is, you can either connect it with a dotted line, or we can connect with a highlighter, which will start making a mess of our picture. So I'm going to use a dotted line. And maybe if you're doing this with pencil, you just go really lightly with your pencil. Because this is not part of my graph, I'm just going to use this as a guideline to make my graph. Okay? Once I have cosine in there, remember where my cosine has zeros or hits my midline because this one is shifted, that's where my secant is going to be undefined. So I know my secant function is going to have asymptotes here where I hit the midline and here where I hit the midline. And then I'm going to have parabolas in between those asymptotes, and the vertices of the parabolas are the maxes and mins of my cosine. So for example, this is my minimum. That's going to be the vertex of my parabola, which is going to go the opposite direction that cosine was going. So instead of my cosine's going this way, I want to go the other direction. So I'm going to go like this, and I'm going to go like this. And then the same thing over here. This one's going to go up this way, and I don't have to go the other way because I'm only graphing from 0 to 2 pi. And then this one's going to go like this. And we did it. Okay, and let's go ahead and confirm with the calculator that our picture looks good. And so let's put in y equals 1 plus 3 times the secant of x. And yeah, looks good. Okay, so let's try this again. Now, different directions this time. We're trying to graph one cycle of this thing. But remember, we're going to use cosine as our reference, okay? So I want to look at the related cosine wave, which would be -2 times the cosine of, I got to factor this thing so I can see b and c appropriately. This would be x plus pi over 2. So I know I'm going to have an amplitude of 2. I know it's going to be reflected. And I know that this changes my period. So my period, which is normally 2 pi, is going to be cut into 2 cycles. So my period is going to be pi. That's how long it takes for one to happen. And that's important because we're just graphing one cycle. And then here I also can see my phase shift. So I have a phase shift that's going to take this graph to the, remember when we were adding, we're going in the negative direction. So we're going to go to the left pi over 2. Okay, so I'm trying to graph a cosine curve. It's going to shift left pi over 2. It's not going up or down. So I don't want to move my midline this time. I want to move my my y-axis reference line. So left pi over 2 means we're going to start here. I'm going to use this dotted lines because it's not part of my graph. And cosine is supposed to start at its max. This one's going to start at its minimum because we're reflecting, and that minimum is going to be -2. So we're going to start, that's my eraser, down here. And then it's also going to end there, but the question is, where does it end? So remember, our period is pi, so the cycle is going to end in pi radians. So I can see pi is, this whole length here. It's like 2 half pi's. So if I go the half and the half, I'm going to end up here for the end of that one cycle. Okay, so that's the end of my one cycle. And in between those minimums is going to be the maximum of 2. So right in between is going to be on the y-axis. That's going to be my maximum of positive 2. And then in between those is where I hit the midline, which will still be my x-axis. Okay, now I'm going to erase this because I'm going to have to put asymptotes in here, and I really don't want to make a mess of my graph. And it might have been okay to leave it, but I want one cycle of my secant, so I'm going to use my one cycle of my cosine that I have in here as my reference. Okay, so there is one cycle of cosine. So secant now, that's the one that I actually want to graph, is going to have asymptotes where cosine is equal to 0, because the reciprocal of 0 is undefined. So the one I'm trying to graph, my secant, is going to have an asymptote there, and it's going to have an asymptote there. Then in between, it's got parabolas, and I'm using my maxes and mins as my vertices. So my graph that I'm trying to make, what color did I use? It's going to be my red one here. It's going to have a vertex here, and we're going to go the opposite direction the cosine curve is going. So it's going to look like that. And then vertex here, opposite direction that cosine is going. Vertex here, opposite direction that cosine is going. So there we have one cycle of the secant curve just based on using that cosine curve. Okay? I know, it's ugly, but it is what it is. So let's look at once we've got this one down, the cosecant function, basically exactly the same. So I spared us a little bit here. The parent form for our cosecant function, y equals the cosecant of x. Since, again, cosecant is just the reciprocal of one of our others, it's the reciprocal of sine, then we can also write this as 1 over the sine of x. So I already took the liberty of graphing. Hopefully this looks familiar. This would be one cycle of the parent form of our sine curve. So this one is the sine of x. And we can see exactly what happens. Here is the same thing we saw happen before. Our cosecant function that we're looking at has asymptotes when sine is equal to 0. So here's where the sine is equal to 0. I can see an asymptote in that graph. I can see that the parabolas in my cosecant function can't get there. Sine starts at 0. I can see an asymptote happening there. And then sine ends at 0. I can see an asymptote happening there. And then my parabolas, the vertices of my parabolas have or are at the maxes and the mins of my sine curve. So there's my parabola forming opposite of my sine curve. Here's my parabola forming opposite of my sine curve. So those parabola pieces represent the graph for our cosecant function. So it's a lot going on in that picture, but I think based on the front, hopefully that makes sense. So same types of characteristics, not a continuous graph because it has those vertical asymptotes. This time the asymptotes happen where the sine is going to be equal to 0, and those are easy ones, remember? So we're at 0, at 1 pi, 2 pi, 3 pi, so these happen when x is equal to n pi, every multiple or factor of pi there. And again, n is an integer. And so not continuous because we have those vertical asymptotes. In between the asymptotes we see the parabolas. And then the vertices of the parabolas are the max and min points of our sine wave. Period, still 2 pi. No x-intercepts, no max, no min, no amplitude. That terminology doesn't apply. Domain is all the x values except for the ones that make 0 in the bottom of the fraction. So we cannot be n pi. Again, that's for n is an integer. I'm sorry I didn't put that in. And then the range. Again, everything outside of the typical range from -1 to 1. So sines in there from -1 to 1. Reciprocal are, what am I saying? Yeah, the reciprocal, sorry, of sine is, I'm like, what am I, sorry, this threw me off here. I forgot to change that. I was copying and pasted from the front. This should say cosecant. I was like, did I just do all the wrong stuff? Cosecant. Goodness. Reciprocal of sine. Anyways, so this range is the outside of the -1 to 1. So again, everything from -infinity to -1, united with everything from +1 to infinity. And then sine we saw as an odd function having that symmetry about the origin, the same will be true here. Secant is an odd function having that symmetry. Oh, copied and pasted. Symmetry about the origin, which means when we plug in a negative x, copied and pasting. If I take the cosecant of a negative x, I get a negative result, negative cosecant of x. So every point in its opposite. So when I think about the cubic function, one that we know, right? 1 cubed is 1, or negative 1 cubed is negative 1, or 2 cubed is 8, negative 2 cubed is negative 8. That's what's happening here. If I take the cosecant of an angle, a positive angle, I get positive. Take the cosecant of a negative angle, I get negative. Okay? Alright, so I'm sorry for the copy and paste issues. Now, let's try to graph. Transformation rules apply, but the easiest way to do this is to start with our sine wave. Start with the sine wave, and then we use that as our reference, and then the reciprocal just goes the opposite directions. So, let's go ahead and try to graph y equals negative 2 minus the sine of 2x over the interval from 0 to 2 pi. So this one is going to shift down to, it's also going to reflect, and then the period is going to change because I got to fit 2 cycles in there. Period is 2 pi divided by 2, so it's going to be 1 pi. So I've got to fit 2 cycles in there from 0 to 2 pi. So let's do it. We're going to shift down to, so I'm going to use this as my midline. Okay, now sine is supposed to start on that midline, so we can go ahead and make that starting point there. And then we're going to go down instead of going up because we have a reflection. And instead of ending at pi, remember because we want to end at the same midline, we're going to end at 1 pi. So one cycle is going to happen from there to there. Amplitude didn't change, amplitude is still 1. So from the midline, we're going to go up 1. Maybe I switched these graphs because this is really tiny. And then in between, oh, sorry, we reflected. So down 1, and then, oops, this is one cycle. Start and stop on the midline. In the middle is the midline. In between those points in the midline, the minimum and the maximum. Oof. Okay, so there's one cycle. Excuse me, let's get another one in there. In between those, minimum, a maximum amplitude of 1. Oof, I feel like I'm gonna cough again. Okay, so this is my sine curve, not my graph. I just want to use this now as my reference. Okay, my reciprocal, my cosecant, the one I actually want to graph first, wherever sine is 0, cosecant's going to be 0, or going to be undefined. So my 0 here, there's going to be an asymptote. And not zeros, they shifted because of, the shift down 2, but the midline, the same thing is going to happen. So where we hit the midline or the x-axis, where we have those zeros, we're going to have asymptotes. So we're going to have a whole bunch in here. Okay, we see a lot more than we normally do because we have more cycles happening here. And then we're going to draw our actual graph now. The maxes and mins being the vertices. So now here's a vertex from my parabola just going the opposite direction as my sine wave. So here's one here, going to go up, and going to go up. Here's another one, sketch that in. Here's another one, and sketch that in. So it should look something like this. Again, this would be great to confirm with the calculator. Let's put in y equals negative 2 minus the sine of 2x. Oh, sorry, not sine. Looking at my writing and not the one that I'm actually trying to graph, which is cosecant. And yeah, 0 to 2 pi. You can see the 2 on the bottom there, and the 2. Yeah, perfect. Okay, so our work is confirmed. And now we just have one more time, one more graph. So again, let's look at this related sine curve. Let's try to look at y equals 3 times the sine of x minus pi over 4. And I don't have to worry about factoring because the coefficient of x is 1. So I can see that I'm going to have an amplitude of 3, and then I'm going to have a phase shift. This one Subtracting means we're going to go in the positive direction, so we're going to go to the right pi over 4. Okay, so I'm going to not move my midline. I'm going to move my y-axis. We're going to go pi over 4 to the right. So pi over 4 is going to be here. We're going to use that as our start. And sine starts at 0. This one will still start at 0 because we're not going up or down. And goes... we're not changing our period either, by the way. So starts at 0, ends at 0. And we're going to end pi over 4 after 2 pi, so we're going to end there. In the middle hits 0, middle's normally pi, so we're going to shift pi over 4 there. And then in between those are maxes and mins. So it's going to go max first because we're not reflecting. Max is going to be 3 this time. So we're going to go, here's the middle, and we're going to go up to 3. And then in between the other two, here's our middle. We're going to go down to -3. And that looks good. So there's one cycle of my sine curve that has an amplitude of 3 and is shifted pi over 4. And this one just, again, says, to graph one cycle, so I'm not worried about capturing everything from 0 to 2 pi or anything like that. So let me just draw this dotted line in. Okay, so I'm going to use that as my reference now. Every place that sine is 0 or hits the midline, which is still 0 in this one, is where my cosecant is going to be undefined. So I already got one in there. That's good. The first one, there's my second one where I'm hitting 0, and then here's my third one. So 3 asymptotes, and then I'm going to use my max and min to get my parabolas. So this, change colors. Parabola here, again, go the opposite direction of my sine wave, so this, something like this. And then over here, my second one, something like that. And let's confirm it, and then we can be done. So we're looking at y equals 3 times the cosecant of x minus pi over 4. And I'm just looking at one cycle with those two parabolic pieces. Yeah, looks good. Remember what one cycle looks like. We did that up here. We see the two parabolic pieces from 0 to 2 pi, so that's what one cycle should look like. Perfect, exactly what we did. Okay, so not the easiest or maybe most fun thing to do, but it's good because we got some extra practice of graphing the transformations of sine and cosine. So we're going to use those. You just got to remember which reciprocal goes with which. So it's sine with cosecant, and it's secant with cosine. So we graph the related sine or cosine curve, and then just use that as our reference, flip all those points, and those zeros are where we're going to have our asymptotes. Okay? Hopefully you got enough to get going in your practice. As always, reach out if you need some extra help, and until next time, take care.